You've probably seen it yourself. You give a large language model a brand new task, something it's never seen before, right there in the prompt, and it just gets it instantly. It feels like some kind of magic, right? This ability to learn on the fly without any of the slow, painful training we usually think of with AI. Well, today we're going to pull back the curtain and see exactly how this incredible trick actually works.
And that really is the central mystery here. How on earth can an AI learn something new in a split second? This whole thing, which is called in-context learning, it seems to just break all the rules. I mean, the model's core programming, its weights, they're supposed to be locked in after training is done. So, what is really going on under the hood?
Okay, let's look at a super simple example to see this in action. We can literally teach a model a completely made-up language. We'll tell it, in Flippertish, a car is a zoop and a tree is a flarn. Then we ask, okay, so what's a book? And you know what? A lot of the time it gets it right. It'll suggest something like glorp. It figured out the pattern from just 2 examples. No huge data set, no hours of training. It just learned.
And this is where the difference becomes so stark. You know, traditional AI training is this slow, brutal, data-heavy process that permanently changes the model. But in context learning, it's instant and it's temporary. As soon as you open a new chat window, poof, it's forgotten all about Flippertish. So if it's not updating its core weights, how is it working? That is the big question.
To find the answer, we have to crack open the engine of the LLM itself, which is called the transformer block. Just think of it as having 2 main parts. First, there's the self-attention layer. Its job is to read everything in your prompt, all the words, the examples, everything, to understand the context. Then it passes that understanding over to the second part, the MLP, which is the bit of the neural network that actually makes the final prediction.
And the answer, according to a really groundbreaking new theory, is something called an implicit weight update. The idea is that the context we provide in the prompt, our Flippertish examples, causes the first part, the self-attention layer, to create a temporary, on-the-fly update to the weights of that second part, the MLP layer. So the model's permanent programming doesn't change one bit, but for this one specific task, it acts as if it has.
Here's a great way to think about it. Imagine a master chef. They have a fixed set of recipes they've mastered. Those are the model's pre-trained weights. You walk in with a special request, which is our prompt. Hey, can you make that dish, but make it spicy? Now the chef doesn't need to go back to culinary school and learn a whole new recipe. Nope, they just temporarily adjust their technique for that one specific dish. That's the implicit weight update.
It's a really neat theory, right? Super elegant. But in science, a good idea just isn't enough. You need proof. So the big question is, how did the researchers actually test if this implicit update was really happening?
So they designed this absolutely brilliant experiment. First, they trained a simple little transformer model to learn basic math functions. Then they set up 2 tests. In scenario A, they did exactly what we did with Flippertish. They gave the model new examples in the prompt and let it learn. Standard in-context learning. But in scenario B, they gave the model 0 examples. Instead, they used their new theory to calculate what that temporary weight update should be, and they just applied it directly to the model's MLP layer.
And the results? Well, take a look at this. This graph is basically the smoking gun. The yellow line shows the model's performance when it's learning from the prompt, and the green line? That shows its performance when the researchers just use their calculated implicit update. They're identical. The theory perfectly predicted exactly how the model would behave. This isn't just a clever idea, it's mathematically real. But they didn't stop there. The researchers found something even more amazing. This quote from their paper basically says that this whole implicit process, it isn't just a one-off party trick. It actually mimics the step-by-step process of traditional training, which is known as gradient descent. In-context learning is, for all intents and purposes, a super fast, temporary version of the real thing. And the evidence just keeps piling up. Look at this. As you give the model more and more examples in the prompt, moving from left to right on this chart, the size of those implicit updates actually gets smaller and smaller. The model is converging on the right answer. It's stabilizing its temporary knowledge, which is exactly what a model would do during a long traditional training process.
So, to wrap this all up, what have we learned? Well, in-context learning is not magic. It's a really clever mechanism. It works by creating these temporary implicit updates to a part of the model. And this whole process acts just like a hyper-fast version of traditional training. Best of all, this whole effect is mathematically predictable, and now it's been experimentally proven.
This discovery is huge, and it leaves us with a really fascinating question to chew on. We've just unlocked a key secret of how these amazing models learn on the fly. But think about it. If an AI can pick up new skills temporarily, without ever having to permanently change its core self, what does that really mean for the future of truly adaptable, flexible, and maybe even creative artificial intelligence?